Hello, I'm Adam Bonomo, and welcome to What's Beyond Today. If you were to guess how far you can see with your own two eyes, how far would you guess? Well, it's actually dependent on your height, which is, if you're about 6 feet tall, you can see just over 3 miles away. If you were to look up at the night sky, you're able to see light from stars that are roughly 4,000 light years away, with little to no clarity. Although, today, we're able to see things that are much further away, such as galaxy GN-Z11, which measures in at a whopping 13.4 billion light years away. So there's quite a discrepancy there. What made it so that we were able to look so far into the universe? The first person to start peering into the cosmos with their own telescope was Galileo Galilei in 1609. He wasn't the first person to develop the telescope. That was lens maker Hans Lippershey the year before him in 1608. Galileo was a person who refined it to the point of practical use, and he was also the first person to make major discoveries. The types of telescopes they were using were called refracting telescopes, or telescopes that use converging lenses to magnify an image. To put it simply, light would go through a larger lens, then into a chamber, and be focused onto a smaller lens, resulting in a magnified image. Now, Galileo's telescopes weren't seeing 13.4 billion light years away. They were only able to see about 9 to 20 times what we're able to see with our own eyes. But with that, he was able to find some really cool things, such as the phases of Venus, the craters on our moon, 4 of Jupiter's moons, the rings of Saturn, and also gave us the understanding that our solar system is a part of a much larger entity, our galaxy. Pretty far out for just some lenses in a chamber. Over the next century, there are major changes to the telescope, but the main thing that was discovered was the more refined light is, the better image you'll receive, thus the further you'll be able to see. The first person who would try to discover different ways to improve on this phenomenon would be Johannes Kepler, and he would start bouncing light around more in his telescopes, using a different eyepiece lens as well as adding a prism. Up until this point, telescopes were simple and lightweight, but Kepler wasn't married to that idea. Instead, his were much more bulky and stationary. With this, Kepler discovered the 3 laws of planetary motion, which essentially just hammer home the idea: the Earth is not the center of the universe. The next person to really take a stab at this refining process would be Sir Isaac Newton in 1668. Instead of sending his light through a bunch of different lenses, he would refine his light using mirrors, which would be a huge factor when it came to looking out into the cosmos. These types of telescopes are appropriately named reflecting telescopes. This would be a huge revolution, and it would make it so that we had another tool when it came to designing telescopes. Newton discovered that the rules that govern the universe around us also govern us here on Earth. We'll get more into that next time. There wouldn't be a major addition to telescopes until the late 19th century, when observatories would make their first appearance, being these huge buildings dedicated to refining light, no longer encapsulated by a chamber, but instead housed in a friggin' building. The two that we're going to talk about today were, weirdly enough, both used by Edwin Hubble, a big name in the world of finding cool stuff. The Yerkes Observatory Telescope and the Hooker 100-inch telescope. The main difference was the Yerkes was a refracting telescope and the Hooker 100-inch was a reflecting telescope. Also, at this point, telescopes were able to take pictures. That was huge. That was a really big deal. Anyway, the main MVP of this whole situation is our guy, Edwin Hubble. With these observatories, he discovered the atomic explosion of a star, found the first globular star clusters, the way stars moved, and also found the rate of expansion of our universe, which was huge for us. The universe is constantly expanding? Using this information, as well as these special types of stars, Edwin Hubble was able to determine the distance between galaxies. We were also able to start stationing telescopes in outer space and having them send information back to Earth. That's pretty neat. Now, there are a bunch of primordial versions of these, and we're not going to get into all of them. The one that's my favorite, and honestly is one of the coolest projects we've ever done, is Voyager 1. In 1977, NASA was trying to study the outer solar system. So they shot this telescope into outer space, and then it sent its findings back to us. It found a thin ring around Jupiter, 5 moons for Saturn, and it gave us a much better view of the outer solar system. It's actually gone so far, it's not even in our solar system anymore. The main reason why it's my favorite, though, is it has this beautiful golden record on it that's constantly playing, and it really encapsulates what it means to be an Earthling. Recording of a mother and baby interacting for the first time, a whale singing, laughter, an engine starting, thunder, heartbeat, hello, in a bunch of different languages. It is seriously such a beautiful undertaking. Just in case it was ever found, there are these celestial coordinates on it that they could trace back to where the satellite originally came from. In the 20th century, we started looking out into the cosmos with telescopes that saw beyond our visible light spectrum. Which we should probably detour real quick and talk about the spectrum of light because it's really important as we start to move forward. Anyway, light is a wave, right? And waves have these things called crests. And depending on how far away these crests are from each other determines what type of light they are. Okay, so look at this. Things on the left here, this is going to be blue shifted light. This is going to be light with the smallest amount of space between crests. And things here on the right, that's going to be red shifted light. That's going to be light with the most space between crests. See the small little sliver right here? That's visible light. Everything you've ever seen is in that small little sliver of light. Although luckily, we have made tools that are able to translate other forms of light into our small little sliver. Now we could get into X-rays, gamma, and radio telescopes that we've made over time, but they just haven't found anything that's that interesting yet. Okay, time to get to how we can see 13.4 billion light years away, and also the most prestigious telescope we've ever launched to date, the Hubble Space Telescope, named after no one other than our guy, Edwin Hubble. Launched in 1990, and roughly the size of the school bus, the Hubble is still used today. Sent in a low Earth orbit, in the vacuum of space it uses two mirrors to see inconceivably far away, as well as across a spectrum of light. Which is hype. That's awesome. That's really good. Also, we have to go over a couple more concepts real quick because they're really important. First up, the Doppler effect. Discovered by Australian physicist Christian Doppler in 1842. He found that as the source or the observer of light gets closer or further away, it changes the distance between the crests of the light. As things get closer, they become blue shifted. As things get further away, they become red shifted. Second up, Einstein's theory of general relativity, in which he tells us about the universe expanding, causing objects, or in this case galaxies, to move away from each other. Furthermore, any light in that space will also stretch, making it be much more redshifted. This can make distant objects dim, or impossible to see at visible wavelengths of light, because as it's traveled all this distance, it's become redshifted and turned into infrared light. Okay, those are those two concepts. It wasn't that hard. Look at you. I'm proud of you. That's why it's important that the Hubble can see across a spectrum of light. Going from 0.1 to 2.5 microns of space between its crests, it can go from ultraviolet all the way to infrared light. Also, up until this point, I've been talking about how important it is to see things in infrared, but how about I just show you? Okay, so here are two pictures of the same nebula. One of them were taken with the visible light spectrum, and then here's one with the infrared. Do you see how many more stars you can see in that? Also, not only can infrared see these more stretched out waves, but it also doesn't get blocked by space dust, which is exactly how it sounds. It's not the most climactic ending to their triumphant journey, but a lot of stuff goes on in space, and a lot of dust gets left behind. My favorite picture that the Hubble has given us is the Hubble Deep Field. You see all that? Those aren't stars or planets. Those are entire galaxies. When you see it, it just makes you feel so small. The Hubble has helped us determine that the age of the universe is 13.8 billion years old, as well as shown us how a galaxy and solar system are formed. Shows us what happened when a star burns out. Well, if a star burns out. A star can end in a huge, fiery explosion, or it could collapse in on itself and turn into a black hole. All of this was found with the Hubble, and it can see galaxy GN-Z11, the current bar for how far away we're able to see, at 13.4 billion light years away. Although, how can we see beyond that? How could we push the bar further? This brings us to the main topic today, Hubble's successor, the James Webb Telescope. Named after James Webb, NASA's administrator when we landed on the moon. The James Webb isn't supposed to replace the Hubble. Instead, it's supposed to work alongside it. The James Webb isn't going to be in low Earth orbit either. It's going to be at L2, one of the 5 Lagrange points. These areas are about 1 million miles away from Earth, having this perfect balance of gravity between the Earth, the Moon, and Sun, giving the satellite perfect orbital motion. This telescope will be further away from the Moon than the Moon is the Earth. The James Webb uses a series of 18 mirrors that have this honeycomb design to them. The telescope is also much more focused on redshifted light. The Hubble is able to see from 0.6 to 2.5 microns in the infrared spectrum, but the James Webb is able to see from 0.6 to 28 microns, which is so much more. It's not using 30-year-old technology, it's using state-of-the-art stuff. It will be able to see things that are invisible to the Hubble. And with this technology, we're hopeful that the James Webb will be able to find the first galaxies that ever formed, because the further away you can see, the further back in time you can peer. It could change our perception on the beginning of the universe. It could change the way we see the universe, period. If we look at how each of these telescopes revolutionized the way we see the cosmos, we can only speculate what we're going to find with the James Webb. Luckily, it launches on December 22nd. It's going to take about a month to reach L2, then 6 months after that to set up. But then, boom! We can start using the next most prestigious telescope ever developed in human history. I can't wait to see what we find with it. Now, what if we were able to look at the universe not with light, but with gravity? We'll talk about that next time. Thanks for watching. I'm Anna Bromo, and that's what's beyond today.